Let us understand the next type of fault, that is line to line fault on an unloaded synchronous generator. So here you can see to that the generator which is grounded through a neutral impedance means the reactance. Okay, and here it is assumed that the phase B and the C are get short circuited. Okay, so based on this we can see to that the thermal conditions. So here already we understood that the healthy phase of that current will become zero, means the where does the fault is not takes places, the current across that phase will become zero. Okay, so that is Ia is equal to 0. So here there is an the fault between the two phases. Okay, the phase B and the phase C. So consider together IB plus IC will become 0. Okay, so from this we can write it as IC is equal to, it is minus of IB. Okay, one is forward, another is a reverse path. Okay, so one is carries and another one is which is opposite to that of the phase value of the current. Okay, so then it is the meaning that the what is the voltage across the B will become same as the C, and what is the voltage across C will become same as the VC. Okay, call this equation as 3. Okay, that is IC is equal to minus IB, and the call this equation as 4, that is VB is equal to VC. So from this what we can see to that here, so I told that previously, so based on the terminal condition only we need to find out what is the symmetrical component relation. So here it is very difficult to calculate that either the voltage and the current. So however we can do a judgment that by looking at the equation 3 we can see to that already Ia is 0 and IB it is the minus of IC, or the IC it is minus of IB. So it mean that at least any one of the value of the phase current is become 0. But here if you looking at the equation 4, it is VB it is same as the VC and the VC it is same as the VB, and we don't know what is the condition for the VA. So that's why we are trying to calculate the value of the symmetrical component of the current. Okay, let's see to that. So based on this equation 3, okay, what is IA naught? We know that it is 1 by 3 times IA plus IB and IC. So what is IA? It is already 0. Okay, IB exists, IC we can write it as from the equation 3, it is minus IB. So hence IB minus IB will become 0. So you'll get IA naught, it is 0. Okay, and what is IA1? IA1 it is 1 by 3 times IA plus A into IB plus A square into IC. Okay, so we know that what is IC? It is minus IB. Okay, so that is nothing but A minus A square. So you'll get A minus A square IB. Okay, and similarly what is IA2? IA2 is nothing but 1 by 3 times IA plus A square IB plus A into IC. Okay, again substitute that IC value, so that is nothing but minus IB value, so you'll get A square minus A. So from these two equations what we can write it as, so what we know that what is A minus A square, that is J root 3. Okay, what is A square minus A? It is minus J, okay, J root 3. Okay, because already we know that. So from these values we can write it as IA naught is 0. What is IA2? IA2 can be written as minus IA1. Why? This is a plus J root 3, this is minus J root 3. So based on these two equations, okay, IA1 is equal to, it is A minus A square IB, IA2 is equal to, it is A square minus A. So based on this what we can write it as IA2 is equal to minus IA1. Okay, so it is a meaning that the value of the zero sequence voltage will become 0. Why it is 0? Because IA naught is 0. So here there is a presence of the value of the positive and the negative sequence voltages. Why? Because so from this equation what we can understand it is one is a positive, another one is negative. So based on this what we can see what is the relation between these two. Okay, so no need to calculate that what is the VA naught value. because IA naught is already 0. Okay, so what is VA1? VA1 is 1 by 3 times VA plus A into VB plus A square into VC. Okay, so from equation 4, what is equation 4 says that is VB is equal to VC. Okay, so VC can be written as VB, that is nothing but A plus A square. So that is nothing but we know that A plus A square. So equation 1, because that is means this equation. So we know that 1 plus A square is equal to 0. So this equation can be written as A plus A square is equal to minus 1. So that is nothing but A plus A square can be written as minus 1. So this equation will become 1 by 3 times of VA minus VB. Okay, call this equation as 5. So what is VA2? VA2 is nothing but 1 by 3 times of VA plus A square into VB plus A into VC. Similarly, we know that what is VC? So that is nothing but it is VB. Okay, similarly, so A square minus A. Okay, sorry, that is nothing but yes. Okay, so this that is A square minus A, because so what sorry, A square plus A, that is nothing but VB. So we know that A plus A square can be done is minus 1. So this will become VA minus VB. Call this equation as 6. So by using this equation 5 and 6 can be written as, okay, so that is nothing but VA naught is already 0, because we know that what is VA naught? VA naught is equal to minus IA naught Z naught. So what is IA naught? All IA naught is already 0, hence this will become 0. And so from the equation 5 and 6, what we can write it as, it is VA1 is equal to VA2. Okay, so from this we can write it as the interconnection sequence network. So whatever the voltage across the VA1, it is same as the VA2, but here the current which is carrying from the VA1, it is IA1, from the VA2 it is IA2. Okay, however, there is a presence of the value of the zero sequence voltages, but it is short circuited. Okay, so that's why we are connecting this the network zero sequence network separately, and it is short circuited on itself. So we can see to that VA0 it is consisting of IA0 and Z0 value, and it is short circuited by its own network. Okay, so VA1 is equal to VA2. We can write it as, what is VA1? It is EA1 IA1 Z1, and for the VA2 it is IA2 Z2. Okay, so this is right side arrow mark, this is left side arrow mark. Okay, from this what we can write the sequence quantities is, okay, so IA1 is equal to minus IA2. Okay, so it is opposite to that of the polarity. So what is IA1? IA1 is nothing but, what is the source of impedance is, means source of EMF is EA, and the impedance is the total impedance. Okay, so it is Z1 and Z2. So IA1 can be written as minus IA2, the source of EMF divided by total impedance. And what is IA0 VA0? That is going to become 0 because of the current, it is 0. Okay, so we are interested to calculate to know what is the value of VA1. Okay, so we know that what is VA1? VA1 is equal to EA1, that is equal to EA1, it is same as E A, okay, minus IA1 Z1. So what is that VA1? From this equation we know that it is VA1, it is same as the VA2. Okay, so that's why we are writing it is VA1, it is same as VA2. Okay, that is equal to EA minus IA1 Z1. Okay, substitute this, what is IA1 value? We know that IA1 value is EA divided by Z1 plus Z2. Okay, after doing simplification we will get A multiplied by Z2 divided by Z1 plus Z2. Okay, so we are interested to calculate to know what is the value of the fault current. Okay, consider that the value of the fault current across the B or across the C. Okay, if you consider across the B, this will become IA0 plus A square IA1 plus A into IA2. If it is IC, this will become A into IA1 plus A square into IA2. Okay, so already we know that what is IA1? It is equal to minus IA2. Okay, so we can write it as IA2 can be written as minus IA1. So from this equation, okay, from this equation we can write it as it is minus IA1. So this will become a square minus a into IA1. Okay, we know that what is a square minus a, so that is minus j root 3 into IA1. Okay, so consider that what is the magnitude of the value of the fault current. This will become j, means this will become root 3 times of IA1. What is IA1? From this equation we know that that is EA divided by Z1 plus Z2. Okay, EA divided by Z1 plus Z2. So that is the value of the fault current. So this is the expression for the fault current that we need to remember. Suppose if the neutral is not grounded, what will happen? Okay, we know that Z0 is equal to Zg0 plus 3Zn. So Zn will become infinite. So finally we will get infinite. But the thing is that, so the equation, above equation, that is the value of the fault current is independent on the value of the Z0. Means in this equation it is not depending upon the value of the zero impedance. Hence, whether it is grounded or not grounded, it won't make any effect on the synchronous generator. Consider next a fault, that is double into ground fault on an unloaded generator. Okay, consider this figure that, okay, there is a fault which is takes places between the phases B and C, and it is grounded because it is double into ground fault. So based on this, and also we can notice that it is grounded through a neutral impedance. Okay, so based on this we can write this, the terminal conditions. Okay, so where the fault is takes place between the B and the C. Okay, so and it is grounded. So what will happen if it is grounded? The voltage across the two phases will become zero. So that is VB and the VC will become zero. Okay, and the current of the healthy phase, that is IA, will become zero. So from this terminal condition we can notice that it is very easy for us to calculate that the value of the phase voltage in terms of the symmetrical component other than the values of symmetrical component currents. Okay, so that's why we are calculating the symmetrical component value of the voltages. Okay, so we know that what is the VA naught, that is 1 by 3 of, okay, VA plus VB plus VC. Already VB and the VC it is 0, so that's why we'll write it as it is 1 by 3 times VA1, sorry VA. Okay, for the VA1 it is 1 by 3 of VA plus A into VB plus A square into VC. Okay, so this is also will get 1 by 3 of VA, and for the VA2 it is 1 by 3 of VA plus A square into VB plus A into VC. So this is also will get 1 by 3 of VA. So it is a meaning that the all the symmetrical component of the values of the voltage which is a presence. Okay, so from this we can write it as VA0 is equal to VA1, that is equal to VA2. Okay, so it means that it is equal to, it is 1 by 3 of VA. Okay, and already we know that what is IA. IA is equal to 0. It is a meaning that the value, if the presence of the symmetrical component of the voltages which is a present, it is a meaning that the symmetrical component of the phase current also which is a present. Okay, so from this equation, okay, so consider this is equation 7, because it is VA0 is equal to 1 by, if VA0 is equal to VA1 is equal to VA2, so that is equal to, okay, that is equal to, it is 1 by 3 times of VA. Okay, and so call this equation as 8, that is IA0 is equal to IA1, that means IA0 is equal to IA0 plus IA1 plus IA2 is equal to 0. From this equation 7 and 8, okay, so it is suggest that the network should be connected in the parallel, because the voltages is, it is 1 by 3 of VA. Okay, the voltage is divided, the voltage which is divided to across VA0, VA1 and VA2, and the current is going to add up. Okay, so based on this equation 7 and 8 we can write this interconnection sequence network which is connected in parallel. Okay, so VA1 it is consisting of value of the IA1, and VA2 it is consisting of the value of IA2, and VA0 consisting of IA0. Okay, from this what we can write it is sequence quantities. So that is nothing but we know that, okay, from this above equation what we can write it is VA1 it is same as the VA2, that is same as the VA0, because all the things are connected in parallel. Okay, we know that what is VA1, it is EA1 minus IA1 Z1. What is EA1? So it is same as EA. Okay, so based on this let us calculate that IA1. Okay, what is the source of EMF? It is EA. Okay, the impedance across that phase, and the total impedance, the Z2 and Z0 which are connected in parallel. Okay, let's see that IA1, the source of EMF, and the impedance of that network, and the total impedance of the other part of the network, means Z2 and Z0 are connected in parallel. Okay, similarly what is IA2? IA2 is minus IA1 Z0 divided by Z2 plus Z0. Okay, so how we got this? So let us understand that this is the, okay, incoming current, that is IA1. Okay, so this is the branch current IA2 and IA0. Okay, to calculate the branch current we should know, we know that the applying the branch current formula. Okay, branch current is equal to total current. Okay, incoming current it is minus IA1, the impedance of the other branch, that is Z0 divided by total impedance. Okay, similarly for the IA0, what is incoming current is IA1. Okay, impedance of the other branch it is Z2, and the total impedance, that is Z2 and Z0. Okay, Z2 plus Z0. So we'll get this equation. Okay, so based on this we wanted to know what is the fault current. Where does the fault which is takes place? The fault which is takes place between the IB and the IC. Okay, IB we know that what is IB? IA0 plus A square into IA1 plus A into IA2. So IC value is IA0 plus A into IA1 plus A square into IA2. Okay, what is the common here? IA0 here, we can see to that. So this will become, it is 2 times of IA0. Okay, so here this is IA1, it is A square, and it is A into IA1. Okay, A plus A square into IA1. Similarly, so for the it is A into IA2, and it is A square into IA2. So we'll get A plus A square into IA2. Already we know that. Okay, so that is 1 plus A square will become 0. So based on this we can write it as A plus A square will become minus 1. Okay, substitute that, we'll get the value, it is minus IA1. Okay, because A plus A square can be written as minus 1. And similarly for this, so you'll get minus IA1 minus IA2. So what is the common here? It is minus. So you can write it as IA1 plus IA2. Okay, so from the sequence network we know that. Okay, so that is nothing but already we know. Okay, IA1 plus IA2 is equal to IA0. Okay, so how do you got this? From the sequence network. So you can see here the interconnection sequence network with the current is IA1 plus IA2, which is entering into the network, that is IA0. Okay, this is IA2. It is adding up, that is IA1 and IA2, it is adding up, and it is same as the IA0 value. Okay, so from this what we can write it as IA1 plus IA2, that is equal to IA0. Okay, so that is nothing but IA1 plus IA2 can be written as it is IA0. Okay, it is the value of not the plus. Okay, this is the value of minus IA0. Okay, so from this what we can write it as, this equation can be written as minus of minus. Okay, this is going to plus, so we will get 3 times of IA0. So we know that what is IA0. Okay, from this equation what is IA0? IA0 is equal to minus IA1 into, okay, Z2 divided by Z2 plus Z0. Okay, Z2 divided by Z plus Z2 plus Z0. Okay, so I told that clearly the fault current equation should consisting the value of the relation for the zero sequence impedance. Okay, so what will happens if it is not grounded? Okay, the Zn will become infinite, so hence Z0 is going to be infinite. Okay, so substitute this value in this equation, 1 divided by something infinite, so this is going to be 0. If there is a fault which is takes place on a double line to ground and a single double line to ground fault on a synchronous generator, okay, if it is not grounded, the fault current will become 0. Next type of fault, that is three-phase fault. Okay, consider that the phase A, B and C which is faulted. Okay, so based on this we can write this terminal condition. Before that there is a grounded through the neutral impedance. Okay, so based on this we can write that the terminal conditions are, because this is the three-phase fault and it is not grounded, so IA plus IB plus IC, it is going to be 0. So because of this, what is the voltage across the VA? It is same as VB, and also it is same as the VC. Okay, and from this what we can see to that, so by these terminal conditions it is not possible to either to calculate the voltage or the current. Okay, because it is mainly depending upon one to the another one, but however we can see to that it is IA plus IB plus IC is equal to 0. Okay, so based on this we can trying to calculate the value of the symmetrical component of the current. Okay, consider that, okay, convert this IB and IC in terms of IA. So taking IA as the reference, we are going to draw this IA. Okay, representing in, this is the positive sequence value of the phase sequence current. Okay, clockwise representation, this is IB, and the clockwise representation IC. Okay, the angle between the IA and the IC, it is 120, which is in anti-clockwise direction. Okay, the phasor representation which is in clockwise direction. Okay, this is IA, this is IB, and this is IC, clockwise direction. Okay, the angle between IA and the IC, okay, means the angle which are considering it is in anti-clockwise direction. Okay, so IA and the IC, it is A. Okay, so that is nothing but IC can be written as A times of IA, and similarly the angle between IA and the IB, that is A square of IA. Okay, it is in terms of anti-clockwise direction, so IB can be written as A square of IA. Okay, we know that the value of the symmetrical component, so that is IA1 is equal to 1 by 3 times of IA plus A into IB plus A square into IC. Okay, so substitute this IB value in terms of IA, so this is IB can be written as A square of IA, so we'll get A cube into IA. Similarly, what is IC in terms of IA? That is A into IA, so we'll get A cube IA. Okay, A cube is nothing but it is consider it is as 1. Okay, so this also 1, we will get it is 3 times of IA, 3 will get cancelled, so we'll get IA1 is equal to it is IA. Similarly for IA2, it is 1 by 3 times of IA plus A square into IB plus A into IC. Substitute this IB in terms of IA, you will get A to the power of 4 IA. So this is IC, it is nothing but A into IA, so you will get A square IA. So A to the power of 4 can be written as A cube into A, so we will get A into IA. Okay, this is already, there is a square into IA. So we know that it is 1 plus A square. So this is nothing but the value will become 0. So IA2 will become 0. Similarly for the IA0 is equal to 1 by 3 times IA plus IB plus IC. So already we know that the value of IA plus IB plus IC is equal to 0. From where I got, that is from the terminal condition. So we'll get 0. So from these three equations, what we can see, it is IA2 is 0, IA naught also 0. Only there is a presence of IA1 that is equal to IA. So from this what we can understand is that positive sequence component of the current which is equal to the phase value of the current. Okay, this is the positive sequence value of the current. It is equal to the phase current of IA. Okay, from this what we can write is, okay, call this equation 9. Okay, from that equation 9 can be written as, what is VA1 means, because of the presence of the IA1 we need to calculate what is the VA1. Okay, VA1 is equal to 1 by 3 times of VA plus A into VB plus A square into VC. Okay, so that can be written as already, because VA it is same as the VB, that is also same as the VC from that equation of the thermal condition. Okay, VB and the VC values are same. Okay, what we'll get, it is 1 plus A plus A square, that is nothing but VB is equal to VA, that is a VC is equal to VA. Okay, we will get VA divided by 3, so this value will become 0, so hence VA will become 0. Already VA naught and VA2 is equal to 0 because IA2 and IA naught already 0. Okay, so from this what we can write, it is, we know that what is VA1, VA1 is equal to EA1 minus IA1 Z1. What is EA1? That is same as the EA. Okay, anyhow VA is 0, so this is 0, so this is can be written as EA minus IA1 Z1. So we need to calculate what is the value of EA. Okay, so this will become EA divided by Z1. So this is the equation for the value of the sequence network. Okay, so based on this what we can write here is, okay, so there is a source of EMF and the current which is flowing is IA1 and Z1. Okay, so this is the condition based on this equation. Okay, and here VA0 and VA2 already 0. Okay, so we need to calculate what is the value of the fault current. So there is a fault is either across the IA or IB or IC. So already we know that from that equation. Okay, call that whatever 9 equation 9. So this can be written as, because we know that already we derived that the positive sequence component of the current is equal to the phase current. Okay, so that is IA1 is equal to IA. Okay, so where is we wanted to know what is the value of IF. IF is equal to IA1. So this is the condition for the fault current under 3-phase fault on a synchronous generator. So here grounding or not grounding of the neutral point does not have any impact of the fault current in the case of the 3-phase fault on synchronous generator. However, the fault current in the 3 phases are equal in magnitude but are displaced from 120 degree from each other. So it can be observed that from the circuit, which is similar to that of the steady state model of the synchronous machine, neglecting armature resistance, the positive sequence impedance of the machine, which is equal to the synchronous reactance, that is Z1 is equal to